Hi there, this is Richard Walker from Lucidate. Welcome to this fifth video in Lucidate's series on AI and computer vision. In the last video, we delved deeply into the maths behind neural networks, specifically the use of calculus and the backpropagation algorithm to optimize the network's parameters. In this video, we'll first build a neural network and train it to identify images of clothes. We'll see how easy it is to build AI using modules of Python code. These modules have been developed by large tech companies, Google, Facebook, and Microsoft, all open source their code for others to use. All technology follows a cycle of deployment, evaluation, and improvement. In that respect, AI solutions are no different from traditional technology. However, AI can adapt and improve when presented with new data. So this cycle is typically much tighter for AI systems. To get the best out of AI, we develop evaluation and interpretation tools to leverage faster improvement. For most AI deployments, we'll split our data into two unequal groups. The largest group will be our training set. This will be used to optimize the weights in the network. We'll shuffle up our training data and use it multiple times. Each training sample is called an epoch. Once the weights have converged, we'll run our held-back testing set through the network to see how good the network is on examples that it has not encountered. We'll introduce three visualization tools in this video: a performance chart, which helps us when training the network, a confusion matrix, which helps us understand how good the trained network is on our held-back test data, and a prediction histogram. This enables us to see how confident the network is in its classification. So far, we've discussed a lot of concepts, but we haven't spoken about implementation. How actually do we build, train, and run a neural network? This turns out to be very easy. Over the past decade, many firms have built strong AI capabilities. They have decided to open source their machine learning libraries. Alphabet Google has released Tensorflow, Meta Facebook has released PyTorch, and Microsoft has released CNTK. A popular AI interface called Keras has been built to easily access these libraries. This allows firms like Lucidate to create very simple GUIs to build, train, and test neural networks. I'm not fond of showing code on screen, but I hope you will allow me this time, as I'm doing it to show you how little code is required. And also, the code maps very closely to the way that we've been talking about neural networks. This code is Python, and this handful of lines is all that is required to build, train, and test a neural network using the Keras API. The first line of code is split over 4 lines on the screen, just to make it easy to see what's going on. Here we set up the layers of the network. An input layer, which flattens the 28 by 28 pixel intensities, 2 hidden layers of 128 and 64 neurons, and an output layer of 10 neurons. If we want more layers, we just add more lines of code like these. And if we want more neurons, we just tweak these variables. Here we also specify the activation function, in this case, ReLU. The next line is more complicated to look at, but all it's really doing is setting up the cost function, not as scary as it looks. We're on firmer ground with the next line. We get to choose how many epochs we will train for, and we get to say what the training inputs and outputs are. With our network trained, we can now see how well it performs on our test data and print out the results. Pretty straightforward. Thank you, Keras. Firms like Lucidate can then write applications with user interfaces that populate these functions. Here we can see a GUI to choose the dataset, specify the activation function, input the number of layers along with the corresponding neurons, then train and test the network before saving the results. So we can build a neural network with a few lines of Python code or with a simple user interface. Once we've trained it on a dataset, we'll want to visualize the results. When we're training a network, how do we know when to stop? Should we train for more epochs, or have we already optimized the network's weights and biases? Also, How confident are we that the network can generalize? Overfitting is the phrase we use when a network gives impressive results on the training data, but is unable to replicate these results on data it has not seen. To answer all these questions, we consult a performance chart. You'll recall that we originally split our data set into a training set and a test set. To build a performance chart, we further divide our training data into a training set and a validation set. Hold back our validation data until the end of each epoch, and then we use this validation data as a mini testing batch. We'll record the cost function and the accuracy for the training and validation set at the end of every epoch. The accuracy is a percentage of correct answers. The cost function, if you recall, is a single number showing how far we are away from an ideal classifier. We can plot the resulting curves on our performance chart. Here we can see the improvement in accuracy of both the training and the validation set. When we see flatlining in the accuracy and cost plot, we can conclude that our weights are optimized. We can also look for overfitting. Large divergence between the training and validation data indicate that the network is not generalizing well. We'll discuss techniques to reduce overfitting in future videos. The performance chart makes use of our training and validation sets. But what of our test set? How can we make use of this and visualize our results? One of the best ways is to deploy a confusion matrix. At its simplest form, a confusion matrix provides a way of visualizing a binary outcome. A simple example would be the result of a diagnostic test. A patient either has a condition or they don't. A test will seek to predict whether the patient has this illness or not. There are 4 possible outcomes: a true positive, a true negative, a false positive, and a false negative. We can use the information in the confusion matrix to determine accuracy. This is the sum of the correct diagnoses divided by all diagnoses. The precision is the true positives divided by all positives, and the sensitivity, the true positives divided by the true positives and the false negatives. Our example is clearly more than a binary choice. We have 10 possible items and 10 possible choices. Rather than 2 squared or 4 outcomes, we have 10 squared or 100 outcomes. Finally, there's a great deal of potential information in our output layer. The neuron in the output layer with the highest activation will be our prediction for a given test image. But what about the activations in the other neurons? Might there be information there? For some purposes, there may be. A confident network might be expected to have an activation of 1 in a single neuron and 0 everywhere else. A network that is clueless might have an activation of 0.1 in each of the output neurons. Here's an example where the network has been presented with images of shirts. Neuron 7 is the neuron that will fire if the network classifies the image as a shirt. You can see that the network correctly classifies all of these images. The first image in the top left has an activation of very close to 1 in neuron 7, very confident. But look at the lower 2 images in the middle column. While the network does correctly identify these images as shirts, the output is not 1 in neuron 7. In both cases, neuron 5, which looks for coats, has high activation. Looking around at other results, you can see further examples where multiple neurons were firing in the output layer. The neuron with the maximum activation will be our estimate, but for some purposes, we can make use of the lower activations in other neurons. This is Richard Walker at Lucidate. In this video, we looked at building and training a neural network to recognize images of clothes. We saw how simple it was to develop AI solutions using the open source libraries of big tech companies. We also looked at 3 examples of visualizations of neural networks: the performance chart, the confusion matrix, and the predictions histogram. Given the adaptive nature of AI, the fact that it can improve as it sees more data, it's important to make use of these tools to help us to continue to refine and improve our machine learning algorithms. Please join me in the next video as we apply these tools to our trained network.